Hi folks, we're going to take a look at number 11 from page 451. So here they're giving us equations of two lines. One's in vector form, one's in parametric form, and they want us to determine the value of k, which we see appears in the direction vector, that first line, where the lines are parallel and where they're perpendicular. Okay, now since we're talking about the lines being parallel and perpendicular, it makes sense to work with the direction vector. So we have this direction vector here. What we should do is, so let's call, I'll call this M1 is given by k plus 1, 3k plus 1, and k minus 3. And now let's determine the direction vector of the second line. Okay, so here we know that the direction vector is just going to be given by the coefficients of the parameter. So this is going to be equal to -3, -10, -5. Okay, so if the lines are parallel, it means the direction vectors are parallel, meaning that they will be scalar multiples of each other. Okay, so what we're going to do here is solve. So for part A, determine value of k, is we need to find what value of k will allow these to be parallel. Okay, in other words, for M1 to be equal to some constant multiple, some scalar multiple of M2. All right, and we'll see if there's one unique solution, if there's more than one solution. So let's try to solve this here. So what I have is I have the x component, k plus 1, would have to be equal to some multiple of the x component of the second direction vector, and so on and so forth for the other components. So 3k plus 1 is going to have to be equal to -10 times this scalar multiple, and then we've got k minus 3 is going to have to be equal to -5a. Okay, now one thing I see here is I see three equations with these two unknowns. The best I can do is solve two of them at one time. So I guess let's start with that. So if I take the first and the third, okay, I can solve this system of equations. To make it easier, I got the two k's. That's why I'm choosing the first and the third. So here we'll just put this here. K minus 3 is equal to -5a. And let's solve the system as we normally would. I'll eliminate the k, so I'll subtract here. So I end up with k minus k is 0. 1 plus 3 is 4. And then here -3a plus 5a is 2a. So the a value is going to have to be equal to 2. But of course, what I'm looking for is the k value. So I'll stick the k value into this equation here. So k is equal to, so -3 times a, which is, we just found out was 2, and then I'll bring the 1 to the other side, -1. So here we get -6 minus 1 is -7. Where we have to be careful, though, is that we've only solved the first and third equations. I need to make sure that this same value of k and a will make the second component work, okay? Because there's no guarantee that I can ever make these two lines parallel. I need to make sure that it works with all three of the components, not just the x and the z. It also has to work for the y component. So let's see what happens here. If I take the left-hand side, what do we get? We get 3 times k is -7 plus 1, and we get -21 plus 1 is -20. And then when I take the right-hand side, we get -10 times a, which we found was 2, which is also equal to -20. Okay, meaning that when k is equal to -7, we can rewrite this first direction vector as 2 times the other direction vector, meaning that the lines are parallel. Okay, so a bit of work to do on this one here. So let's take a look at part B. Okay, now in order for two lines to be perpendicular, well, the direction vectors are also going to be perpendicular. And of course, we know that two vectors that are perpendicular are going to have a dot product of 0. So what I'm going to solve here now is I'm going to solve m1 dot m2 is equal to 0. And hopefully that'll allow us to find the k value that makes this possible. Okay, so in the first one, parallel, we had to be able to write the vectors as scalar multiples of each other. In part B, perpendicular, we use the fact that the vectors have to have a dot product of 0. Okay, so let's do that here. So we've got k plus 1, 3k plus 1, k minus 3. Oops, there we go. Dotted with -3, -10, -5 has to be equal to 0. So let's solve this here. So let's multiply the x components. So we have -3k minus 3. So I'll do the distribution all at once, plus the product of the y components. So we have -30k, and then here minus 10. And then finally, we add the product of the z components. So we have -5k and then plus 15, because it's -5 times -3 equal to 0. So let's bring together all the k's. So -3 minus 30, -33, minus 5 is -38k. And then we'll bring the constants to the other side. So -3 minus 10 is -13, plus 15 is 2. Bring that to the other side, -2. So k needs to be equal to -2 over -38. And we can reduce that to 1 over 19. Okay, so we find here that there's only one k value that would make these two lines perpendicular, and that's what makes the dot product of the direction vectors equal to 0. Okay, so again, just to recap, when you're trying to show or look for vectors, or in this case here lines being parallel, the direction vectors have to be scalar multiples of each other and perpendicular. The dot product of the direction vectors have to be 0. Okay, that's it for this one.